Hey, it's Mrs. Gregg. Let's talk about how to separate mixtures. So filtration is one process that you can use whenever you have what we call a heterogeneous mixture. And a heterogeneous mixture is one where you can see the two components of the mixture, they don't mix well. So a really good example would be sand and water. If you have that mixture, you can see the sand, you can see the water separately. So if you were to pour that into a filter, you could think like a coffee filter that you use at home. If you had a mixture of water and sand and you poured it into a coffee filter, then the water would come right through and the sand would be caught in the filter. So filtration is good for separating insoluble solids from a liquid. And that's where we have heterogeneous mixtures. Okay, the next example is called distillation. This is good for homogeneous mixtures or solutions. And here what happens is that you are separating the liquid from the solution. So a good example of that type of mixture or solution would be salt water. If you were to take a box of salt and start pouring it into water and you stirred it up, as long as you didn't pour the entire container in there, then the salt would dissolve well in the water to the point where you wouldn't even be able to see the salt. It would just look like pure water. So that's a good example of a solution. You can't distinguish the two components from each other. They mix really, really well. So if you wanted to separate that, you can't take salt water and pour it into a filter and expect that the salt's going to stay behind. What you have to do instead is, there are a couple of things you can do. One is distillation. So there you take the salt water, you heat it up, and you have a way to collect the vapors that boil off as you start heating. And as you're heating that water, what boils off is absolutely pure water and it leaves the salt behind. So those vapors, as they're rising up, they can be collected in a tube. You can run some cold water on the outside here, and that will cause those vapors to condense, and then you can collect that pure water that would boil off from that saltwater solution. So that's an example of distillation. You can also use distillation if you have two liquids that are soluble in each other. So an example would be alcohol and water. They mix really well and they have two different boiling points. Alcohol boils at a really low temperature. So if you have a solution of water and alcohol and you subject it to heat, then that alcohol is going to start boiling off first and it's going to leave the water behind. And so similar situation, as the alcohol rises up, it condenses, you can collect that alcohol and you'll have pure water left behind. All right, so that's distillation. On to kind of a variation of distillation is called evaporation or crystallization in your textbook. And there, it's good for separating a soluble solid from a liquid. So we could go back to salt water. If we have a solution of salt water, we could, if we wanted to collect the salt and save the salt, and we don't care about the water, then what you can do is boil that saltwater solution, and it will drive the water off. The water will evaporate and it'll go out into the room. You'll have water vapor in the room, and then you'll leave behind salt crystals that you can collect. So you use evaporation or crystallization if you don't care about collecting that liquid and you just want the crystals out of it. Okay, and the fourth separation technique that we're looking at is called sublimation. You don't use this one too often. This is good whenever you have a mixture of different solids and one of those solids will sublimate. So we have to refresh back to physical science whenever you were in 8th grade, where we talked about sublimation, or maybe, yeah, I guess it was 8th grade, you talked about sublimation. So in that case, we're talking about a change of state. So if you have a solid and you heat it up and it goes directly to vapor and bypasses the whole melting situation, it doesn't go through the liquid phase, then that's what we call sublimation. A really good example that you might be familiar with would be dry ice. So dry ice is just solid carbon dioxide. And if you have to keep it at really cold temperatures. If you take it out and you put it at room temperature, then it starts sublimating. It starts putting off these vapors. You might see people use it at Halloween to give you that spooky effect of kind of like fog everywhere. So that's an example of sublimation, going directly from the solid phase to the vapor phase. So you can use sublimation if you have a combination of different solids and one of them sublimates. So the example we have here is if we had sand, salt, and ammonium chloride all mixed together. You could heat it up a little bit and that ammonium chloride will sublimate. It'll go directly to the vapor phase. And then we can collect, we have the vapor phase that would be caught in the funnel here. and it would be cooler temperatures up here. So then that vapor would start to deposit. We would have deposition. That vapor would start to deposit, and we would collect solid ammonium chloride here on the edges of the funnel. And then what would be left behind would be the sand and the salt. And then the last one that we're looking at is chromatography. You've maybe done this before, where you can take a water-soluble marker and then you put a little line on maybe a coffee filter or a piece of paper, and then you can drop that in a glass of water. Don't get the marker in the glass of water. The marker level should be just above the glass of water. And then as the water rises up that paper, it picks up the pigments that are in the marker, and then those pigments will spread throughout the paper. So what we're looking at here, this is a final product where you've used like a black marker, and the line would have been here, and you would have put it in the water, and then as the water rose up the paper, up the filter paper, it would have spread out the pigments that were in that marker. And so you can see all the different colors that would actually make up a black colored marker. And chromatography is good for separating the parts of the mixture that are either dissolved in gas or liquid. And we'll focus on liquid because that's pretty easy to understand. So the mixture would be the marker, and you draw the marker on the piece of paper, and then you set the paper in water, and as the water rises up the paper, it's going to separate out those pigments that are in the marker. This takes advantage of the fact that different pigments in that marker have different rates of solubility. Some pigments are more soluble in water than others, and then some pigments want to adsorb or stick to the paper easier than others. So you take advantage of the fact that there are differences in solubility in the different pigments that would make up the black marker, and then there are differences in the way those pigments want to stick to the paper. Some want to stick to the paper and don't want to move. Others don't want to stick to the paper so much, so they will freely ride up that paper with the water as you're performing the chromatography. And then here's another example. You can do something similar with plants. If you were to crush a plant, and you get the pigments, you get a sample of that crushed plant, you can smear it on a piece of paper, and that's what we're seeing right here. And then you stick that piece of paper in water, or here we're using alcohol, because the plant pigments are not soluble in water very well. They work better with acetone or an alcohol. So here we're using acetone. And then as the acetone travels up the paper, it picks up the pigments that would be in that plant, and it carries it with them. So then the final result would look something like this. Those pigments that adhere to the paper really well, they stay down here. Those pigments that are have larger molecules would stay down here. They wouldn't travel as far. Those pigments that don't dissolve very well, they're not very soluble, they would stay down here. And then those pigments that are more soluble, those pigments that don't adhere to the paper very well, and then those that are made of smaller molecules, those would travel further. And then you could see the example here with the plants. You can see the different types of chlorophyll that would be found in that plant leaf. So these are different types of pigments again. This is very similar to the marker situation I was just explaining, only they're using acetone for their solvent instead of water. Okay, so what are some practical applications for chromatography? Why would you want to separate out pigments? Well, for one, you could do that if you wanted to figure out what types of ingredients made up a flavor or a scent or a color in something. And then another thing, let's say that you had a pollutant and you wanted to figure out what the components of that pollutant are. You could run it through chromatography like that, and based on where the different parts of those pollutants landed on the chromatography paper, how far they traveled, then you could tell what types of pigments. You could use that and compare it against a standard, figure out what types of pollutants you have. Another thing would be if you were looking for drugs in urine, if you're doing drug testing, they can take urine and put it on chromatography paper and separate it out. And if there were a certain drug present in your urine, it would show up at a certain spot in the chromatography paper. And they would be able to identify what type of drug that is based on where it landed on the chromatography paper. All right, so that's it for separation techniques. I will see you in class. Bye.